Thank you. I have a small announcement. First, I'm a tiny bit ill, so there might be once or two times that I will cough to microphone. Sorry for that. Okay, so today I'm going to talk about exactly this, machine learning on streams of data. Attending some of the presentations today, I know that streaming is a big thing now. Was the first presentation on the in the big room about streaming and building machine learning models on streaming. By the way, thank you that you are all here. I know that there is Cloudera there speaking, so I would like to be there, so thank you twice that you are here. Okay, so maybe I will introduce myself. No, it doesn't work. Okay. We'll handle. Oh, yeah. So a few words about me. Like, the last line is the most important. Currently, I am a happy Scala hacker and machine learning expert at Scala. I've been doing quite a lot of gigs related to machine learning. So I've been building recommendation systems. I've been building data pipelines and machine learning solutions for different applications. But currently, I'm like most partial to Scala, functional programming, and of course, machine learning. Okay, so let's have a quick look at the overview of the whole presentation. There are actually three areas that I will discuss today. You can see four, but the last one is like with a kind of smaller font. One is streaming, the other is machine learning, functional programming, and big data, which is distributed programming. You probably know the joke about big data, that big data is like teenage sex. And everybody discusses it, and everybody claims the person like have been doing that, but actually no one knows what it is. So this is big data, right? No one knows what it is, but pretty much everybody knows what's distributed computing. So yeah, I will say a few words about that. Okay, so I perceived this presentation as a challenge, and I had like an issue how to compose it, because there are three big areas. There is machine learning, there is streaming, and there is functional programming. And actually, each of those areas deserve a separate presentation, right? And I want to combine them into one presentation, and I want to convince you that like all those technologies and all those concepts and all those ideas can work together to build great systems and machine learning models on streaming. So yeah, it's a challenge, and maybe at the end of this presentation I will say I'm sorry, but I hope I won't say I'm sorry. I hope I will say you're welcome. Okay. So let's start with streaming. Okay. There is this question: why streaming and what is streaming? We'll start with why. Why? I won't give you the answer. I will give you the use cases. Like, there are even areas where streaming is in the name of this field, like clickstream. I mean, it's literally there. Okay, so there are clickstream, there are financial data, demand and supply, and so on and so forth. And I think that the last one is the most important because reasons. I mean, when you go to Neo4j, for example, conference, they will say that like everything is a graph. Everything is a graph. Graph is everywhere. Okay, I will say that stream is everywhere. Stream is actually everywhere. So, well, it's a little bit of an exaggeration, but you will find that most applications actually employ some kind of streaming. And if you want some more formal definition, I may say that, of course, streams are easily parallelizable and work well with functional programming. Oh, by the way, do you recognize this guy? Yeah, you recognize this guy. This is Keanu Reeves. Keanu Reeves is famous for being in some strange places. Like, people see him on bus, and they see him on subway, and maybe on a plane, but in the budget part. So whenever you see the picture of Keanu Reeves, you should think, maybe I know that guy, or maybe I know this concept, right? So if I say that streams are easily parallelizable and work well with functional programming, well, there is one concept that fits into the definition. What can we exchange streams into? I think that we can say big data. Well, distributed computing, right? So, okay, so we will be talking about streams, but it will often refer to big data or distributed computing. Just to have like the background for streaming, I just would like to say what a stream is. And a stream is exactly this, source to sink, okay? So we have some kind of source that produces or sends data, and there is some kind of sink that receives data, and that's all. This is stream. Like extremely, extremely simple. If we want to make it a bit more complex, we have like source, and then we have this kind of flow. I actually haven't invented that term here, that it fits here. It's from Akka documentation. If you know Akka a little bit, you know that some parts of the stream are expressed as flow. So these are the parts that actually modify and process the data. And we have sink. And there are three really important things about streams. And if you remember those three things, I believe that you can undertake any kind of discussion about streaming. The first one, stream is infinite. So the data just flows. It doesn't have any beginning and it doesn't have any ending. It may have, of course, and we may be aware of that, but by definition, it's infinite, right? When we say that it's finite, it's no longer stream. It's batch. And the second one, it comes with unbounded preceding. And by definition, and by the second one, we go to the third one, it goes into unbounded following, which means that we are unaware what will come. Or we are unaware how much data we will receive. And that's all. And you know everything about streams, in my opinion. There might be some people who disagree with me, but in my opinion, you will actually know streams now. Okay, so before we start our discussion on implementing machine learning on models on streaming, there is this question here, and I would like you to ask yourself that question. Like, if we build streaming applications, because we have all those applications like click streams and financial data and that kind of workflow, why we still use batch processing for machine learning? Why? Well, actually, I believe that you can find some good reasons. By the way, I do it all the time, myself. But think about that question for a while. It may seem reasonable to build a machine learning model on a batch processing and then apply it to streaming application. But there are reasons why you shouldn't do that. Well, of course it works, and it works fine, and actually it's proved that the results are accurate. But when we think about it, when we think about data that is processed in a stream, it's unpredictable. I mean, we cannot predict what will happen. We are unable to accommodate for changes in data because it's streaming. But there might be a change. I will depict it to you like this. There might be a change in the world. There might be a zombie plague, right? Or there might be a nuclear Armageddon, right? Believe me, that will influence the data you receive into your system. I mean, can you imagine zombie plague not influencing the data you receive into your system? And still, you use machine learning model that you trained yesterday to accommodate for zombie plague. Oh, of course, I'm exaggerating. It won't be a zombie plague, I hope. So with that in mind, let's try and build a machine learning model that is learnable, or that can be easily, actually I was thinking about if the word learnable is the best word here, that can be retrained online, okay? By the way, as I mentioned in the beginning, there are like three big areas, so I will jump from subject to subject sometimes, so if you feel confused, please do feel confused sometimes with the slides. Next slide. Okay, so what we can start with? We can start with choosing technology, and there was a lot today talking about Spark and Flink and Storm, and Wojtek said that Spark is horrible. I disagree with Wojtek. I think Spark is really trash. is like atrocious. Spark is atrocious. I mean, well, we all use Spark. I use Spark. But sometimes I need to go to the source code, and it's atrocious. Believe me. I mean, it works, and it works fine. So we have the Spark, we have Flink, we have Storm, we have like Autosportus and Aramis of the big data world. But there is this silent D'Artagnan, like a little bit in the back, right? And the silent D'Artagnan is actually technology that is not that well known in big data world, distributed computing world, which is Akka. Well, you may have heard, if you are really interested in Spark and Flink, you may have heard about Akka. Spark was based on Akka in some ancient times. There were parts that were dependent on Akka. Flink actually depends on Akka. They have their own implementation of Akka called Flakka, which is Flink and Akka combined together. I tried to Google out Flakka some time ago, and it turns out there is this new kind of drug in the United States that is called Flakka that makes people go crazy. They undress themselves and they attack other people in streets. And there's so much news about it that I couldn't find even a single thing about Flakka being a Flink and Akka. It's rather all about that drug. Okay, so I will try to convince you that Akka is actually fully capable of undertaking some, or actually all the things that the other technologies can do. I will try to do that. And, well, yeah. I think Akka, you might find Akka interesting. At least, if you want to use it in production, you might find Akka interesting. So what is Akka? I think I should pronounce it Akka, but yeah. It is what it's here. I won't read it. You can find it on Akka webpage. These are the main selling points of the technology, right? So it's simpler concurrent and distributed systems, resilient, performant, elastic and decentralized, and it has its own incarnation in the form of reactive streaming data applications. Attention, ta-da! Does it remind you of something? Distributed, concurrent, oh, maybe I shouldn't use concurrent, but it's concurrent, maybe parallel, resilient, performant. Distributed computing, big data, right? So it's actually capable, as I mentioned, of undertaking all the tasks that are that are performed by those processing engines that are related to as big data. Okay, so we have technology, we know what streams are, we have the data, and we have the whole setup. We can start building a machine learning model on streams. How shall we do that? I mean, how many ways are there to build a machine learning model on streams? Or machine learning algorithm, doesn't matter. How many ways? I will claim that there is only one way to implement machine learning on streaming and on streams. And in order to prove that there is only one way, I will need to refer to functional programming. So the slides that are coming will get a little bit more difficult with each slide. At the very end, I will say I'm sorry, but I will say it in my own special way. Okay. By the way, I jumped to functional programming, but there is like the very generic thing that allows us to build on streaming, and actually it has been used in machine learning for years, and it's stochastic gradient descent and its versions and its iterations. If you are familiar with backpropagation, then stochastic gradient descent is actually what's used usually with backpropagation, right? We actually update gradients. There are actually some issues with stochastic gradient descent that I would like to refer to, just that we are all aware what's in our way. First of all, there are some things, and these are the treacherous traps I wanted to point to. There are some things that we can't do, or actually things that are extremely difficult to do. And these are the things. I mean, you don't have a batch of data. You have unbounded preceding and unbounded following. You don't know the data. How do you normalize that? I mean, if you don't know the maximum and the minimum because you don't know what will come, how do you normalize the data? How do you input missing data? Well, inputting missing data is like a little bit a different problem here, but how, for example, you may apply dimensionality reduction, okay, to get rid of insignificant features when you do batch. How do you do that? You can't, or it's extremely difficult to do some of those things, right? And all those things happen. Most of those things happen to get into the area of feature engineering. It's difficult to do feature engineering on streaming. There are ways to do that. I will say a few words about them later, but you need to know that if you have a batch model and you have normalization there and you have all that stuff, it might be difficult or impossible to do feature engineering. And there is one more thing, there is hyperparameter tuning, and I will refer to that as well in a moment. I was afraid that that would be the case here. So you probably can't see the arrows. There is one more important thing about stochastic gradient descent. You will usually achieve lower accuracy. If accuracy is something you're after, and you have access to batch, then you would probably like to use batches. There is one simple reason, like when you train on batches, the batch slowly converges to minimum. It gets very close to minimum, and we want to optimize for minimum, right? We want to find the minimum discrepancy between our model and the real world. And like batch processing can do that. Stochastic processing can do that as well. But the problem is that if you hit the minimum is here. I'm really sorry for the colors here, but the minimum is here. It can even hit the minimum, but with all the noise in the data, it will diverge again. It will circle around the minimum. It will circle around our perfect solution, but actually it will diverge at times. And I will prove that today. Oh yeah, it's not Keanu. Probably you noticed that it's not Keanu. I was actually thinking if I should put half-naked David Hasselhoff into my presentation, but I guess at this time you might be a little bit yawning and a little bit sleepy, and it's after lunch and it's afternoon, so especially for the female part of the audience, this is David Hasselhoff, right? Half-naked. But the important thing about David Hasselhoff is that he plays in Baywatch and he rescues people. And there is one thing that can rescue us when we think about implementing machine learning on streaming. And David Hasselhoff in the picture is functional programming. I mean, I don't want you to think about functional programming as being half-naked David Hasselhoff. Please don't do that. But functional programming is going to save us today. And this is like a very important sentence. This second sentence on this slide. I personally believe, and actually I think, I don't have a mathematical proof, but it might be possible to do that each machine learning supervised problem, like with supervised machine learning algorithm, with backpropagation may be reduced to fold operation. If you are from imperative programming, you may not be familiar with fold operation, so here it is. It's actually from Scala. We have fold operation that has some kind of zero, that has some kind of function that takes that zero object and some other object, and it returns the same type as zero. Don't worry, I will explain it in a moment. Okay, so let's stick to that fold operation for a moment, okay? So what is fold? Okay, fold is an operation that, as I mentioned, takes some initial value. It takes some, can I point it? No, I can't, because it's off. That's why. It takes some zero value, and then it takes a function that takes the zero value and another value, and it combines them, okay? It combines them together, returning the same type. And the circle like starts from the very beginning, okay? So it's actually, when you think about it, it's a very simple operation that concatenates, or I would say maps values to initial value and returns it back. And it goes on a collection. I'm confused myself, sorry. But believe me, I think that by the end of this presentation, you will know that fold is the thing. Oh yeah, Keanu, right? What is Keanu doing here? Well, I claim that this operation is MapReduce operation. There has been a lot of MapReduce today, technologies and MapReduce algorithms and referring to MapReduce. And I believe that this operation is actually MapReduce operation, right? So there is some kind of map state that maps those two values to value B, and then it returns the value and combines the value. Well, frankly speaking, I'm a kind of trickster sometimes. So, not exactly. Fold is not exactly MapReduce. Why? Because this is the definition of fold, and this is the definition of MapReduce. Let's say definition. It's a little bit too big word for those two graphs, okay? So as you can see, this kind of operation, so this MapReduce operation allows you for easy distribution or parallelization of the process, right? You have some value A, you have some value B, and then you combine it. Okay, so all those arrows from A to B, they can be parallelized. Okay, and if you think in terms of Spark, then you have a driver that combines them together and or gets them combined already, right? So that's impossible to do with simple fold, but worry not. Functional programming gives us a solution. By the way, I refer to fold because all the code and all the examples you will see today are implemented in that manner, in that paradigm, and the paradigm of fold. Why? Because I am lazy. By the way, if you ask anybody about the most important feature of any functional programmer, those people are lazy because functional programming is lazy. So, you know, functional programmer, lazy. Remember that. Okay, there is a solution. I just want to give it to you because it exists, right? But as I mentioned, all my examples will be implemented in that simple fold function. It's called fold map. Taking aside the name, it actually looks very, very similar to MapReduce. What it takes additional is the zero value and a function that combines all the values together, right? And I deliberately changed the function symbol here from F to C because it turns out that if you implement 0 for some kind of type and if you implement combine function for some type, you get another concept from functional programming which is called monoid. And looking at some eyes and some faces, I will skip explanation of monoid. It's just something that implements 0 and combine function, okay? So it's a function that allows us to combine two values of the same type. By the way, one important thing is that it needs to be associative. If you know associativity, for example, addition is associative, right? It doesn't matter the order, or it doesn't matter the, the order of the operation, it will evaluate to the same. For example, subtraction is not associative. Okay, so we are equipped with all that functional programming stuff, with fold, or fold map, and monoid, and we feel really powerful. Okay, we feel that we can do that. We can implement machine learning algorithm on streaming. Oh yeah, Keanu, because now. Oh, sorry. Now with monoid and with fold map, it is MapReduce. Okay, so whenever you thought about MapReduce being like, wow, super cool stuff that is completely new and nobody else have thought about it, these ideas are here like for 50, 60 years. And in functional programming, they were for many, many years. Okay, to make things worse, I will present you some code. I will present you first the high-level implementation of machine learning algorithm on streaming. Here it is. That's it, right? This line is actually derived from my IDE, and this line is representation of that line. This is the whole high-level API that I implemented to introduce models on machine learning models on streaming. And actually, I have a source. I have a sink here, so those things that we learned exist in streaming. And I have this. I say via linear model, learning vector, ala delta, and 5. And that's all. If you ship a library to your user, that's all the user needs to use. I mean, can it be more beautiful? Okay, I sound a little bit self-bragging. Okay, but it's actually high-level API. There is some kind of magic happening here. Okay, there is some kind of magic. By the way, there are a few things that I would like to say. Like, linear model is the object that returns the logic for implementing like kind of linear model. Then we have this learning vector. It's just a vector, but it contains. By the way, I suppose I have this here. Oh yeah. So it's just a vector, the class that is storing data x and y, because we need x and y, right? Because it's supervised learning. Then we have optimization algorithm. You may know Ada delta, you may not know Ada delta. Ada delta is one of optimization algorithms. It's actually based on gradient descent. There are other optimization algorithms like ADAM, like AdaGrad, and that stuff. And there is only one thing that we need to pass to that thing, and that's number of parameters that we want to receive. So if you are familiar with machine learning, it's number of thetas that we want to receive out, okay? As I mentioned, there is some kind of magic going on. And this is the magic. This is the most difficult part of code that I will show you today. I won't go into details here, but there are some functional programming techniques that actually make it easy to implement and make it easy to create this high-level, very simple API. And this is algebraic data types, type classes, implicit resolution, and by the way, linear algebra lib. If you know Python, you probably know NumPy. Yeah? Are there any Python users here? Yeah, so you probably know NumPy. If you use R, then you don't have to know anything because R is like vectorized out of the box. And of course, I didn't want to invent linear algebra library for myself, so I used one that's available in Scala. By the way, you can see the implementation of fold here, right? So I create some empty object, and then I actually combine that object. There's this, the logic is hidden in that combine method. Okay, I believe I will skip some part of the presentation. I don't want to get too much into functional programming because I look at you. Now, frankly speaking, I'm really impressed with you because you are not yawning at the moment, right? And I really thought you would be. I mean, like, discussion about type classes is also so thrilling that it usually happens with the bottle of beer because nobody can handle it without any substantial help. But I hope you're not that sloth here yawning, and I see no. Okay, so more interesting part now. I showed you a few pieces of code, right? And you may believe or you may not believe that this works, okay? But I will prove that this works. And I want to show you, and of course this demo will be very simple and it won't prove that the model is accurate, it will just prove that it works and works on Akka. So basically, okay, we have all the imports, necessary imports. We have some line stream, which is the data pre-processing. I need to divide the data and I have to tell what kind of data there is. Yeah. And actually, you can see that the whole model from the high-level perspective, from the high-level API is implemented here, okay? So this is exactly the line of code I showed you. So if you prepare something for a user, think how powerful you become when you operate on with functional programming. You can give something like this to the user, and the user may actually change this implementation of algorithm like this, it's like changing one word in code, okay? So let's run it. By the way, this runs on a Kaggle competition data that is, it's prediction of house prices. And it's really lame because I took only the numerical data, right? So I even I even wouldn't like to submit it to Kaggle because that would be embarrassing. Da-da-da-da-da. Okay, and it produces something, right? It produces something and it produces something quick. And by the way, this is implemented as a fully stochastic process. So it takes an entity after an entity after an entity and trains that model. If you would train that model in, excuse me, if you would train that model in R, with a closed form solution, so only with linear algebra modifications, you would get completely different set of parameters. And then you may say, well, if you're saying so, it means that this model is crap. Sorry, this model is not that accurate. It's less accurate. Of course it's less accurate because it's stochastic. It's fully stochastic, so it is less accurate. I told you that. If you use stochastic processes and if you train on machine learning, the model will be less accurate. And the parameters are completely different. But in my opinion, I won't do that now because I have like our script ready to process the parameters as well. Those parameters are better. Why they are better? Because that's actually the case with Ada delta. It keeps the parameters quite concise. It limits the amount it limits the scale, the range of parameters, how they explode. If you know machine learning, you may say that this is something good because you usually use regularization techniques to limit the parameters, right? So if you want to keep the parameters concise, then you would usually use some technique to keep them concise. This model, unfortunately, I don't have this data. I just for some reason, I didn't put it in the presentation. This diverges from the closed form solution model by about 5%, I suppose. So accuracy is by 5%. Either it's basically lower. Okay. So yeah, this is the code. And knowing that you have enough at the moment, I would like to say a few words about this solution. So when we look at it, right, it was fully stochastic process. What are advantages of the solution? And I believe that the first presentation today, you could see those advantages as well. So the first one is regarding functional programming. So high-level code is clean and readable. And actually, the user needs to change the name of the model, right? It's all. If we provide a number of models, then the user can utilize any of them just by changing the name, and maybe providing different number for a set of parameters. This is something that I skipped. That low-level implementation is highly extensible due to utilization of type classes. And by the way, the most important part of my presentation is that fold instance is intuitive and can be extended to other solutions and technologies. Actually, when you think about that fold operation that we had there, I claim that it can be easily extended to Spark and Flink. I mean, you can take this solution that is here. Of course, it's not. This solution here is a proof of concept, so you just can't take it one-to-one. But if it's like fully ready production solution, you can take it and you can plug it into Spark and you can plug it into Flink and you can plug it into Storm and it will work. Because it's actually a general level idea rather than some kind of implementation detail. Okay, so what are some advantages and disadvantages of those solutions of machine learning on streaming? First of all, I think I haven't mentioned that enough already. When you build a machine learning on streaming, you have a learnable model, right? You have a model that can actually accommodate the changes in the world. So the zombie plague or the nuclear annihilation of the whole race. Well, I think you don't care about your application when there is nuclear annihilation of the whole world, but still. By definition, it also adjusts to changing conditions. This is pretty much the same. But this is something that you gain for free. Because when you build machine learning models on streaming, you actually the models require, or the algorithms require, less computational power. What is the main reason that actually people started performing mini-batch processing on neural networks? Mini-batch processing gives you the ability to process the data that otherwise could not be processed. And mini-batch is actually taking a huge batch of data and splitting it into many, many mini-batches. And if the number of observations within the mini-batch is 1, you are in a stochastic process. So you are in streaming, actually. Okay? And as I mentioned, it's natural for most data. I also pointed to those disadvantages. Okay, it provides less accuracy, although it's not always the case, and we will see in a moment why it's not always the case. And some good feature engineering techniques are difficult to apply. But are we sorry for that? Well, if you are sorry for that, I may remind you that a few years ago, there was no machine learning, no data science, and no deep learning, and all that stuff. There was statistics, okay? I think that some of you may be familiar with statistics, with all the tests, Wilcoxon, something, Coxon, you know, from the names, Shapiro, Wilk, and that stuff, tests, statistical tests. And I remember when machine learning was introduced, everybody was crying, like, how can you do that without the testing? Like, what's the significance of the features and so on and so forth. So I think that we can sacrifice some good feature engineering techniques for more performant and more adaptable machine learning. By the way, we can mitigate those problems as well. We can sacrifice them, but we can mitigate. How can we mitigate? There are techniques I mentioned that I will give you a few techniques that actually can mitigate the issue of machine learning on streaming and stochastic processes. For example, performing mini batches. I mentioned mini batching. Mini batches give you the possibility to, for example, normalize data. It's a completely new set of issues because when you perform normalization in a mini batch, how do you accommodate the fact that the normalization in the other mini batch will be completely different, right? But there is technique for performing mini batch gradient descent. It's absolutely a different kind of talk. I won't discuss it today. It's I will come next year and I will bore you with the mini batch gradient descent then. Okay. The other thing is, it's actually sometimes so obvious that people forget about it. You can't start with a set of hyperparameters like just on streaming. How do you set learning rate? How do you set learning rate on streaming? I mean, you just can't take it out of nowhere, out of thin air. So actually, you need to either update or provide hyperparameters with batch processing. I believe that each streaming should start with batch processing. It must start with batch processing because otherwise you are unable to, in the simplest form of gradient descent, you are unable to find out the proper learning rate. And what if you use Adam? You have learning rate, you have beta 1, you have beta 2, you have alpha, you have fudge, you have like whole set of hyperparameters that are actually heuristics. Okay. Oh, this is interesting. And this is something that Flink advertises, but not for machine learning. It advertises that as the feature that actually enhances the whole data process. You can run different models in parallel, okay? So there is another thing, because what about, as I mentioned, what about this learning rate? You have the learning rate. You know that learning rate, like when you think about gradient descent, that's like the most important thing. Oh, the most important hyperparameter, actually. So what if something changes and the learning rate suddenly becomes insignificant or suddenly becomes wrong? Then you may try to run few different streams, or actually you can learn on few different branches of stream and with different hyperparameters. And of course you can use better optimization algorithms. Okay, so we are going, because I mentioned in the beginning that we have like 3 different areas, so I have to give you like 3 different pros and cons of different things. So there was machine learning on streaming, and now we have Akka. I will just quickly breeze through Akka. What is the main advantage for me and for developers of Akka? You have full control over streaming application. Full control. You have the control of everything. Well, of course there is API, and you use that API to influence, but when you think about Spark and Flink, then the level of control is significantly higher. What is the main disadvantage? Disadvantages aren't here, but what is the main disadvantage of Akka? You have full control over streaming application, which means that there is no Cloudera, Databricks, or data artisans that will take care of the library. You have to do that. You have to take responsibility for the solution. Okay? By the way, when you think about processing engines for distributed computing like Flink and Spark, they have connectors, and I would like to say that Akka also have connectors. The library is hilariously named Alpaca. Okay, so you have different connectors for file system, AWS. Yesterday there was a new version of the Alpaca, and it actually brings the support for Mongo. You have Akka Streams Kafka. This is so significant that it deserves to be a separate library. It has huge community and big number of contributors. Wojciech showed us the number of contributions and issues solved with Spark, and that's really impressive. But believe me, Akka it has huge community, and it's actively developed. It's really actively developed. There are updates and new features quite so often. By the way, this is something I think that the encapsulation for the part regarding Akka is pretty much the same as the previous presenter said. It's like choose technology that fits your needs. Okay, if you want to use Spark, use Spark. If you don't want to use Spark because you're a hipster, then use Flink. Or any kind of, or maybe Storm. And if you are really crazy, but you really want to take responsibility for what you build, and you want to have full control over what you build, use Akka. It will cause you a lot of pain, and tears, and blood. But in the end, you know that that's your piece of code, and that you can influence that, and you can change it. How do you change implementation of a machine learning algorithm in Spark? There is something you don't like, a single line of code that actually mingles with something. How do you change it? Maybe it's a bug. Maybe they know it's a bug. You don't. You actually, okay, you can like fork and you can create your own version of Spark. You can contribute to Spark and then wait for a new release. But you don't have the responsibility for your own software. You have flexibility. And sometimes you have better performance because you can actually very quickly build something on top of it. But you know, that's a burden that has been discussed in IT for years, like so. Okay, I have another demo. I don't know if I have time. I don't have time. And I'm really sorry that I can't show you this demo. It's far more interesting than the previous one, because after the previous one, I really saw some people yawning. But I expected that. It's okay. You can even fall asleep during my presentation. I have another demo. I implemented a neural network on top of streams. And I think that, can I take like 3 minutes more? Is there anybody? Yeah? Okay. So this is not the use case that I invented. It's a use case that was invented by Andrew Ng. Probably you know Andrew Ng. Who knows Andrew Ng? Yeah, most of the people interested in machine learning. And if you are interested in machine learning and you don't know the guy, no problem. So this is the problem. Okay, we need to classify the blue dots and the red dots. Okay, we need to classify if the blue dot is a blue dot and if the red dot is a red dot. Okay, and if you think about simple logistic regression, the accuracy of a simple logistic regression is 47%. Okay, it's like horrible. Accuracy of neural network model developed by Andrew Ng is 91.25. Actually, I suppose it's a very naive implementation, but I also have a naive implementation on streaming. By the way, I'm trickster, so it's not like streaming. It's mini batch. But mini batch on Akka is also very simple. What's the name? Main and then batch. Okay. So you remember, Andrew Ng implemented neural network with accuracy of 91.25. This, what you will see here, is batch processing. It's batch processing. Okay? So it's not streaming, it's batch processing. Okay? We have a cost, doesn't say us much. But what we have here, the final accuracy if we of course multiply it by 100, we have 91.5 accuracy with batch processing, with a very naive implementation of a neural network. Okay, but we also have, neural network, oh yeah, this is it. But we also have the implementation, oh, sorry, wrong button. But we also have implementation on streams. The only difference is it's not like fully stochastic process, because there is one thing, but please do not pay too much attention because I needed to make some tricks to repeat to provide a loop for putting the same data into the stream. But the important thing here is that, as you can see, we have, by the way, there are 400 entities there. So we have grouped them by 100, okay? So we have a kind of mini batch. I know I've been talking about stochastic processes, but this is something that you may consider legitimate when you want to cheat a little bit, okay? Okay, so this process is stochastic-like, and it takes a moment. It's slower, but we don't care. Believe me, the implementation is really naive. It was like an evening or two. Okay, final accuracy, 91.25 if we multiply by 100. 91.25. The same accuracy on batch in Python as the accuracy on streaming in Scala for that problem. And this is like the answer to the main question of this presentation. Why you should use batch machine learning techniques if your application, I assume, if your application is based on streaming, be it clickstream, be it fraud detection, be it supply and demand chain, right? I don't know if I proved that it's easy and elegant to perform machine learning on streaming with functional programming, but at least you know now that it's possible, that it's feasible, and sometimes I claim it would be more beneficial for your application. Few things, if you want to learn something more about Akka, if you want to learn something about functional programming, there is really good tutorial. Unfortunately, you need to know some Scala, but there is a really good tutorial by Daniel Westheide. I don't know how to pronounce the name of the guy, but by the way, he created a framework for testing Spark applications. How did he do that? He just copied all the functionality of RDD, but it doesn't need Spark context. By the way, I would like to say that we are, like, I feel really privileged that I could stand here in front of you, and that this conference is like really awesome. There are too few conferences like this in Poland, and we as Scala are really happy that we can support it. There is yet another conference in Gdańsk, but it's related to Scala and functional programming, and if you want to learn something more about functional programming, if you want to visit us, it's the website scalawave.io. It's usually in July. This edition was in July. And that's my Twitter account. Sorry for not posting this presentation online, but if you feel like following me, I will give you a link to that presentation, and I will give you the code eventually on GitHub or on some other repository, I believe. Okay, thank you. Yeah, if you want to ask questions, I would happily hear some.
Does Akka Streams have built-in clustering capability, or is it like multi-node processing?
Yeah, exactly. This is something I forgot to mention during the presentation, actually like Akka Streams itself doesn't have this capability, but Akka Streams come with Akka Actors, so it's rather a toolkit than a framework. So Akka Actors actually, they have the way to distribute, and they have the cluster capabilities. But combining Akka Actors and Akka Streams is a little bit separate issue. So as I mentioned, you have a lot of power, but you know, with power comes responsibility, Pete. So. So yeah, it has this. Akka itself has this ability, this functionality, but it's not like in Akka Streams. Questions?
Yeah, mm-hmm. You were saying about the training, which was actually excellent. I like it very much. I didn't know that well, the stochastic kind of training approach in streams. My question is about, because you say about the training, and the fold you show is in theory infinite. If you have well, yes. The map fold is not, but the fold is in theory infinite if you talk about infinite stream. So how you use it first in general for prediction, whatever you call it.
Yeah, yeah, exactly.
And the other is what about the distributed? Because you started about saying about distributed and then you stopped at some point. Yeah. So yeah.
As I mentioned, I'm a bit of trickster, so I purposefully omitted distribution. So the first question is about being able to predict on that fold actually. So you can modify the. I have been thinking about that, and I've come with a very simple solution. It's not very intricate and it's not very sophisticated. Basically. You can provide the type information with data. And when you provide type information with data, you can actually decide based on the type information what you want to do with the event. So if this is like, I implemented a learning vector, so you can decide that if this is a learning vector, so you have this possibility to push it through algorithm and retrain the model or update the model. And if this is like prediction vector, then you can make prediction on it. So I think that the easiest way to do that is to provide relevant type information. And the second question, oh yeah, like it is possible to distribute it, of course, and we would need to okay. Actually, because the issue is here a little bit broad, in my opinion. Like, first of all, when thinking about functional programming, I would implement it in a case of foldable. So as I mentioned there, and if we think about distribution, we can do it in a kind of async way. So we can distribute it I need to admit that I haven't tested it, but we can distribute it in a asynchronous way and then combine asynchronous values. But I personally would go to Akka actors, as I mentioned previously. So I would distribute the stream itself. Of course, we have like many other issues with that as well. But with a little bit of engineering, I think that it would do the trick. I don't know if the second answer does it answer your question?
Yeah, I think it answers.
Oh, okay. It's certainly trickier to distribute the data in streams and in Akka. So that's an issue. Yeah, I've been thinking about it, but I'm still looking for a like perfect solution, like sweet spot. Yes. Yeah, I suppose.
How do you solve a problem of using the stream, the trained model for the prediction at the same time?
Yeah, that's true. Actually, I may have introduced the wrong wording here, or the wrong definitions here. I think that the way to do it, the clue of this answer is, the way to do it is to provide a relevant type information, and on that type information, you decide what to do. It doesn't have to be separate streaming. Like, it doesn't have to be a separate branch of a stream. Sorry for that. I'm overinterpreted the question. So I believe that in order to decide whether to learn or to predict, you need to pass the type information with the data. And you can actually do that based on some initial criteria when you receive the data.